We're gonna look a different way now at mapping, specifically how remote sensing methods do at mapping the meadow's edge. I'm from MassBays. My co-PI is from MassCZM. That's Todd Callahan, and our contact information is shown there. So the problem we have is a very heavy reliance on remotely sensed eelgrass data for things like project siting and permitting, water body assessments, and restoration planning. But unfortunately, there is a low degree of confidence regarding the exact location of the shallow and deep edges of the meadows. Ultimately, the risk there being inadequate protection of the whole meadow, which can result in net loss over time. The primary question we set out to answer is how accurate are eelgrass maps generated from satellite, airplane, drone, and side scan sonar imagery? More specifically, how does the remotely sensed edge compare to a diver measured edge? At what eelgrass percent cover does each method perform best or worst? And is map accuracy affected by canopy height or patchiness at the edge? Our study site involves 5 sites in coastal eastern Massachusetts, from Niles Beach in Gloucester all the way down to Cohasset, which is just south of Boston. At each of the 5 sites, we acquired imagery via drone, side scan sonar, airplane, and satellite, as well as underwater photo, ground truthing, and diver transects. All of these surveys were completed within a synchronous 4-week window between mid-June and mid-July of 2022. The project has a very detailed QAP, Quality Assurance Project Plan, that you're welcome to dig into if you want more details about the methodology, but I'll just give a very brief overview here. We acquired satellite imagery from Planet. They have a lot of different satellite models, but we took advantage of data from their Super Doves, which are very small satellites. They can fit in the palm of your hand, as you see in the picture there. Planet launches these into space in flocks of hundreds or thousands, and these things are just orbiting the Earth, collecting imagery over our area almost every day. The imagery is 3-meter pixel resolution, which is pretty good. And that imagery was available to our project for free through a NASA commercial smallsat program agreement. And anyone can take advantage of that and apply for it if they're federally funded. Airplane imagery was collected by MassDEP as part of their long-running aerial mapping program that's been going on since 1995. Excuse me. So for this project, we coordinated with DEP on the exact timing of their flights and the exact locations to make sure it was suitable for our study as well. And that imagery is 25-centimeter pixel resolution. You see an example up there at the top of the screen, and it's typically flown with a small Cessna. Drone imagery was flown using an off-the-shelf consumer-grade DJI Phantom 4 drone. This collects 3-centimeter pixel resolution imagery, which we processed in Drone Deploy software. The image you see on the right is the drone taking off at Swampscott Harbor. It just hovered up in the air before going to about 80 meters altitude where it would run its mission. And the picture on the left is a picture from that survey in Swampscott Harbor, where you can really clearly see the eelgrass. You could see mooring scars associated with the boat moorings. And then if you look closely on the left-hand side of that picture, you can even see sort of individual eelgrass shoots through the water column. It's pretty amazing. Side scan sonar was conducted in the field with our field partners at Mass Division of Marine Fisheries. We followed a mow-the-lawn pattern using, again, an off-the-shelf consumer-grade product called the Humminbird Helix 9 sonar. This is really a jazzed-up fish finder that turns out to be really good at mapping eelgrass too. And this provides 50-centimeter pixel resolution imagery, which is stitched together to form these nice mosaics, these bands across the survey area. And in the imagery, I understand it's grayscale, so it could be a little weird to look at, but the featureless darker gray areas are just seafloor, sand. And then these lighter gray, whiter, cloudy, fluffy looking signatures are eelgrass. That's eelgrass. Photo ground truthing involved random haphazardly sampling in the vicinity of the diver transects. And this was using an underwater camera mounted to a 1/4 meter square drop frame. We sampled 30 stations in this manner per diver transect, so 90 stations per site. And at each one of these stations, we recorded eelgrass percent cover using the CMEX bins shown on the table on the top right. And finally, the diver survey, the last piece of the data acquisition. 3 diver surveys were conducted at each of our 5 sites. There were 2 shallow transects and 1 deep transect. And at each transect, the divers would start in the dense part of the meadow and lay a transect out exactly perpendicular to shore, stopping when they found the last chute. They confirmed it was the last chute by going another 20 meters beyond that point in search of other last chutes. And if they don't find any, they come back and put a subsurface buoy there so we can get a GPS fix on that point and work their way back along the transect, laying 13 evenly spaced quadrats along the transect, measuring things like eelgrass percent cover, canopy height, algae and animal presence, quadrat photo, and then something unique for this project was sampling the distribution type, and that's a measure of the patchiness in the area. And I'll talk more about that in a couple minutes. So it's important to note as I continue on my talk, I talk about edge a lot, and there's actually 2 different edges that we're talking about. There's the diver edge, which is that last chute that they found, either along a shallow or a deep transect. And there's also the photo interpretation edge. So that's the edge that the photo interpreter, when analyzing the imagery, the edge that they drew along the boundary of eelgrass based on what they could see in the imagery. So those are the 2 different edges we'll be talking about. And really, one of the primary purposes of this project was to find the difference between those 2. So after all the data are collected, then we have a complete data set for each site. And this is just an example of what that looks like for one site, Beverly. And you see from left to right, the different imagery data sets from the 3-meter satellite imagery, the 1/4-meter airplane imagery, 3-centimeter drone imagery, side scan sonar, and then finally on the right are diver transects and ground truthing points. So this is a complete data set ready for analysis. Photo interpretation came next. All the aerial imagery and the sonar imagery, they were photo interpreted by both an experienced interpreter, and that was me, as well as newly trained partners from 4 different organizations. And so we have 2 complete sets of photo interpretations for all sites. And delineations were drawn out in ArcGIS Pro following a standardized protocol. Again, that's in our QEP. We took advantage of a variety of ArcGIS tools like the histogram stretch seen in the photo here. The left photo is the raw imagery for a site, and then the right photo is just applying a very simple histogram stretch to that photo. It really helps draw out underwater features, and really that's just done by applying some math to all the individual pixels in the raw image. And I just want to note that for the rest of the talk, all of the photo interpretations that I'm going to discuss are going to be those done by the experienced interpreter, or me. The analysis process was done in ArcGIS Pro. First, interpreted polygons were compared against diver measured edges to find that edge error. So those areas shown in orange on the plot on the chart. Next, interpreted polygons were compared against the percent cover data from photo ground truthing and the diver quadrat surveys. This is used to assess accuracy of each remote sensing method per eelgrass percent cover bin. And lastly, we looked at the polygons relative to chute height and patchiness, which were measured by divers to help provide context around the limitations of each method. So let's jump into the results here, starting with the edge error results. So here we're going to be looking at false negatives, and that means points that were not mapped as eelgrass by the photo interpreter, even though eelgrass was present. The different survey types are on the x-axis and mean error is on the y-axis, and the data are separated by shallow and deep edge. Starting with the shallow edge shown in blue, error is lowest for drone imagery, about 11 meters, meaning that 11 meters of eelgrass is missed by drone imagery on average. Error increases with decreasing image resolution, up to 38 meters for satellite imagery. Some sites and survey types, for example, drone and airplane, had close to 0 error at the shallow edge, which was pretty impressive, but just for certain sites. At the deep edge, shown in orange here, error varied by data type, but ranged from 72 to 101 meters. If you note the standard deviation bars, all of the methods had errors at the deep edge upwards of 120 meters from the photo interpreted edge. I was especially surprised that the sonar deep edge was nearly as high as the other methods. I was surprised because one of the strengths of sonar in remote sensing is that it's unaffected by water clarity. So this makes me think that the edge dynamics and density might be just as important as water clarity across the methods. Also, if these numbers were to be translated into management recommendations, such as applying a buffer when using any types of these survey data, we might suggest using those maximum standard deviation values to achieve the greatest resource protection. We're still sort of thinking through that right now, though. Now, in the reality of photo interpretation, there are also false positives, which refers to drawing eelgrass polygons where it doesn't actually exist or overestimating the eelgrass meadow. False positives existed in this project as well. And when we include these in the edge error calculations, the results are a bit harder to interpret with much larger deviations. So the best way to make sense of this is to break it down by site. In this plot, the edge error is still on the y-axis, but on the x, we now have the study sites from north to south going left to right, and as well as depth. And then the series are now the 4 different survey types. Bars above the 0 line indicate those false negatives where eelgrass was not mapped where it should have been. And bars below the 0 line are false positives where it should not have been mapped. Beverly and Nahant were the only sites that did not have false positives. Gloucester and Swampscott had it to a small degree, and Cohasset had more false positives than not. But this makes sense because Cohasset was one of our most troublesome sites, with nearly the entire site dominated by patchy eelgrass mixed with dense macroalgae, so very challenging for photo interpreters. Next, onto the accuracy assessment for percent cover. Just a reminder that the data used for accuracy assessment comes from the interpreted polygons, as well as the diver and the ground truthing surveys. This assessment provides the proportion of points in each percent cover bin that fall within each survey polygon. So for example, with the purple satellite polygon that you see here, how often do the 1 to 10% cover bins fall inside? So these white circles. 100% accuracy would be all 1 to 10% cover points falling within the polygon. So you can clearly see it's going to be less than 100% accuracy. That said, when you lump together all of the sites, the accuracy for each method and for each percent cover bin is shown here. The green color coding is ranking the values in each column or bin. And looking at the rightmost column, we can see that overall accuracy tracked with image resolution, with drone being the most accurate, satellite being the least. And in the leftmost column, we can see that the 1 to 10% cover bin was the most problematic across all survey types. Within that bin, accuracy, again, tracked with image resolution. However, again, there's a lot of site variability hidden within these averages. This table breaks down the accuracy by site and then by survey type. And you can see that some sites did better than others, and this is largely due to different site conditions. So for example, Gloucester in the picture on top, this performed very well across all surveys. But in this location, the edge is fairly abrupt. The eelgrass edge kind of follows the shoreline right at the low tide line. But in comparison, Beverly has a very expansive area of low density eelgrass and more opportunity for mapping error in those lower cover bins. Moving on to the effects of canopy height. These data are from the diver surveys, and again, they're compared to the polygons from each survey. So measurements that fell within a polygon were considered mapped, shown in blue, and those that fell outside of it were missed in orange. So you can see that all methods reliably mapped eelgrass with mean canopy height around 50 centimeters. However, across all survey types, there appears to be a threshold somewhere around 20 centimeters of canopy height, below which all methods may fail to reliably detect eelgrass. Interestingly, drone and sonar were able to detect slightly lower canopy heights than airplane and satellite imagery. We also tested the effect of distribution type. And for this variable, divers categorized eelgrass in the vicinity of each quadrat location as being continuous, where shoots or patches were within a meter of each other, transitional, where they were 1 to 5 meters apart, or patchy, where shoots or individual shoots or patches were greater than 5 meters apart. The plot has proportion of observations for each survey type on the Y and survey and distribution types on the X. Again, the observations are grouped as falling within each polygon, or mapped, or being missed. Oops, excuse me. Starting with continuous eelgrass distribution, which is less than 1 meter separation, all sites performed very well in mapping continuous eelgrass. Sonar did especially well, given its low proportion of misses. In transitional eelgrass, all survey methods mapped and missed nearly the same proportion, with the exception of drones, which performed slightly better than other survey types. And in patchy eelgrass, all survey types performed poorly, with most surveys missing the majority of patchy eelgrass. So to circle back to the questions that I posed in the beginning and some possible answers. How does the remotely sensed edge compare to diver measured edge? All remote methods had edge error. Shallow edge error ranged from 11 meters for drone to 38 meters for satellite, and deep edge error was much greater, from 73 meters for sonar to 101 meters for airplane. So to put it directly, we are missing a lot of eelgrass in our mapping programs. At what eelgrass percent cover does each method perform best or worst? Overall, the ranked accuracy is drone did best, sonar next, followed by airplane and satellite. All remote methods performed worst, where eelgrass cover was 1 to 10%, not too surprisingly, and best where cover was greater than 40%, and unique site conditions greatly affected accuracy results. Is map accuracy affected by canopy height or patchiness at the edge? Eelgrass with mean canopy height about around 19 centimeters or less is less likely to be mapped. Drone and sonar may be able to detect shorter eelgrass. All methods performed well when eelgrass is continuous and poorly where eelgrass was patchy. And in transitional eelgrass areas, all methods miss a large proportion of eelgrass, although drones did perform slightly better. Next steps, we're still sort of in the middle of this grant, so I have more analyses planned, especially around site and depth specific influences on some of the results that we see here. I'm also curious how there could be some interacting influences of things like density and canopy height together, or patchiness and canopy height even. So some more work to do there. I also didn't even get to touch on the novice interpreter work, but I'll be doing some more detailed comparison of experienced versus novice interpreter and have some recommendations about that. So our final report and management recommendations will come out later this summer. And I just wanted to share our link to our story map. It's a great place to go to see, learn more about all the methods of the project, see some fun photo and video media from the field, and to stay tuned for more results. And with that, a big thank you first to our funder. This is a NOAA-funded project under the Project of Special Merit funding program. And then our many, many partners. We had lots of field and data image interpretation partners, as well as advisory committee members and other folks who have helped greatly along the way. So with that, I'll say thank you, and I'm happy to take a couple questions.
Thank you, Jill. That was a great presentation. So I know that this may not be part of the of what you were looking at, but I wonder if you would be willing to give us a personal opinion, knowing how much the cost of each of these techniques may be, and knowing now the error. Do you have an opinion on which would be the most cost-effective method to use?
Yeah, I'll answer just for myself, since I don't want to speak for my co-PI or for the advisory committee or anything like that. But I think satellite imagery has come a really long way, and I think it's a bit of an underutilized resource, especially given that some data sets you can acquire for free now. You could even task a satellite. You could tell it when and where to fly over a site, and it will. So it's sort of this untapped resource that I think we could take better advantage of. But really, no single method is going to get you everything you need. So any method that you choose to go forward with will always have to be supplemented by ground truthing, by maybe bringing in some higher resolution methods where needed. and more of a site-by-site basis. So in a nutshell, that would be my recommendation, but we'll see how that shakes out when we really evaluate, the time and resources that have to go into dealing with the data for each of those.
Well, it's good news that us divers will never be completely replaced, I think.
Never.
Tyler, your question.
Yeah, hi there. Hope I'm coming through. Thanks, Jillian. That was amazing. I work for the Washington State DNR, and there's tons of parallels to some of our recent efforts to use drones and aerial imagery to map eelgrass and kelp forests. And I was curious if you could comment a bit on how you accounted for tides, to what degree you tried to have consistent tides across all the surveys. Thanks.
Yeah, that's a great question. The environmental planning for image acquisition was a major headache, but also a very important part in terms of ensuring data quality. So we had pretty strict environmental conditions where all aerial imagery had to be collected within 2 hours of low tide, and that metric was met, fortunately, including the satellite imagery. So the imagery is so available that I actually had my choice of days. I just had to get all of the data synchronous within that 4-week window to make sure the bed wasn't expanding too much between surveys. And I just had my choice of imagery, satellite imagery. So I was able to put in the parameters of what time of day, what date and what time of day I was looking for, what level of cloud cover, things like that. You could put that right into your imagery query when you're looking for satellite imagery. So I was able to successfully control for tide, fortunately. Some of the other things were less successful. We had sudden winds pop up and clouds come in, but we're able to deal with all those things.
Right. Eric.
Jill, great presentation. I really enjoyed this. 2 questions. Did you select days for diving to have a better assurance of water clarity and fairly calm conditions? And my second question, which is kind of related, is how did you position the sampling that the divers took? Did they tow a GPS alongside the top of the surface? And did you account for offset if you did?
Yeah, those are excellent questions. In terms of timing and water quality, we went around and around a great deal about this. It would have been ideal to have water quality data coupled with every survey type, especially the remote surveys. But because there were 4 different remote surveys happening, we just couldn't figure out the logistics of that type of sampling. So we never did pair water quality data with the imagery data, but we hoped that the environmental constraints that we placed on the methodology would help alleviate that. So there couldn't have been rain or storms within 24 hours, no clouds, no precipitation, things like that, to help control for water quality in that way. But we don't have actual data to ensure that conditions were identical from data source to data source. And then in terms of getting accurate diver locations to put on a map, because remember, they're at the seafloor and they're sampling along a transect at each quadrat. That I did manually in ArcGIS Pro. So I had the start and end points of their transect, and I knew the distance that they traveled to each quadrat. So I was able to add those points somewhat manually. The ArcGIS added them for me, and then I just had to sort of move them to the right distance along the transect to put them approximately where they belong. And I think all of that's done with about 3 meters of accuracy, just based on the common accuracy of a boat GPS unit.
Okay, so that the endpoints were surface marked and you
Yes.
took GPS points off those. Okay.
Exactly. Yep.
Thank you.
Mm-hmm.
Mike Bradley.
Mike Bradley at the University of Rhode Island. Just a way just to introduce myself. I've done a lot of the aerial mapping for Rhode Island and in Long Island Sound, so I really appreciate your talk. I have a number of questions. Number one, did you alluded to the fact of some different sort of habitat characteristics among your sites, and I wonder if some of that would be related to anchored macroalgae and rocks, and if you were able to discern any differences among your methods for differentiating between eelgrass and macroalgae on rocks, because as you know, that is really a difficult thing to discern on many occasions. Number two, were you able to look at the efficiency across your methods? In other words, Phil alluded to the cost, but it's really cost per acre. And so that would be something else that, you know, that's a question that I know you get and I've gotten several times. And sorry, I'm just going to ask one last one, and you can choose to not answer it if you want to, but did you look at the spatial accuracy of specifically the drone imagery? Because I know that that can be pretty difficult sometimes to georeference, as well as the side scan sonar imagery. And with that, I'll take my answers off the air.
Yeah.
Thanks.
Yeah. Nice to meet you. These are all great, very relevant questions. Let me start with algae first. So the only method that appeared to do pretty well with discerning algae is the drone imagery. Just because of the super high resolution, you can actually pick out the different colors of algae. You could pick out ulva, as long as you're shallow enough, you could pick out ulva compared to brown algae and red algae and eelgrass. It's really incredible how easily discernible those are. And I can't say that any of the other data types have that level of detail available. So if we were able to note that, it was really only through the ground truthing or the diver data that we're able to tell the difference between, know that there was even algae there. And it was quite problematic, especially for that one site in Cohasset, where the whole bed is like, 20 to 50% cover and just mixed with macroalgae and kelp and giant tufts of ulva, and just very, very problematic. And the bottom type is also different there. So rather than a sandy bottom, that's more of like a gravelly shell hash, which just made the whole site very, very difficult to map with all imagery sources. So yeah, challenging. I can't say we came up with a solution for dealing with underwater rocks and algae, but I can say that the drones perform best in that regard. You're gonna have to prompt me again with the topic of the other two. Oh,
Sorry.
the efficiency. No,
Sorry,
that's okay.
I gave you a lot of questions there. I apologize.
I remember the efficiency question. So we're going to get to that in the reporting, because you're right. It's not just cost, but there's logistics to it. There's ease of dealing with the data, and there's scalability. So we're going to get to all of that in our final report and recommendations. But off the bat, having flown the drone a whole bunch at these, site by site areas, that's not something I see producible at a statewide scale, for example. It's kind of a burden. You're chasing the tides. You can only cover a small area at a time. It has to be line of sight. There's just so many limitations to it, but it's an incredible tool for, project by project type scale. And you mentioned accuracy of some of the mosaic data, like side scan sonar and the drone imagery. So we relied on proprietary tools for that, like Drone Deploy, which has gotten very, very good at stitching together tiles even over the water where it has nothing to georeference. It's just using the corners of the picture and the GPS point and the altitude. It's gotten very good at that, but it's not perfect. But I will say it is very, very good at the land side, the shallow edge side. And I confirm that by comparing it to something that is geo-referenced out there already, something reliable like the USGS color ortho imagery. I'll make sure that there's landmarks in the USGS imagery that are positioned exactly where they are in the drone imagery. And then with side scan sonar, that's a little bit more of a crapshoot. Unfortunately, there's not a great way for correcting and confirming that, since it's underwater imagery. You don't really have landmarks to check against. And this being just an off-the-shelf mapping tool, that Hummingbird sonar unit, we can't assume that it's perfect. And I think we could probably do a little more work, putting some targets out and mapping and seeing how well it does. But for the first, broad brushstroke pass at this, it did pretty well for the project, and we feel fairly confident about the accuracy of where the data landed on the map.
Right. Kayla. Kayla, you're still muted. There you go.
Hi, Kayla Sullivan, EPA Law and Sound Office. I might have to wait until you produce your recommendations, but I was just curious about the ground truthing component and the further application to, the entire MassBays. I know it was just 5 sites. So do you think you're going to have different ground truthing recommendations for sites that might differ in patchiness and that can't be picked up all the way by satellite imagery? Like, what does that look like for the entire application to your whole estuary?
Yeah, that's a great question. I think the project has definitely shown that more ground truthing at those edges is imperative. That is most likely going to be one of our management recommendations that we make to Mass DEP to make sure that their ground truthing effort that supports their aerial program is really targeting those areas adequately. But really, when it comes to practice, rather than necessarily changing the methods that people use, we might be able to instead implement, the use of management buffers, where if a construction proponent comes to you with a drone polygon, an eelgrass map based on drone imagery, you might go to those error bars and, apply a buffer around what they've provided, just knowing that there's some error and variability. So that might be more of a likely recommendation. It's something easier for folks to take up than altering, the way they implement monitoring programs.
All right. I don't see any more hands up. So I want to thank all of our speakers because I think all the talks today were outstanding, thought-provoking. They fit together nicely. So I think they all did a great job. So as a kid, I used to play a lot of basketball, and the guy who ran the gym would say at the end of the day, you don't have to go home, but you can't stay here. So I will end today's session with that wise advice. I want to thank everyone for coming, and pencil in on your 2024 calendars the last Wednesday of March. Tay, go ahead. You have a question?
Sorry, I'm trying to clap for you, Phil. Thank you.
Oh.
I didn't mean to raise my hand, but great conference. Thanks very much.
All right, everyone. We will see you next year.
Thank you, Phil.
Thanks,
Great.
Phil.
Good job, Phil.